My research period started. Not everyone know me, so I have to a brief presentation of myself. I started to work on research in 50 years ago at the Norwegian Defense Establishment, Kjeller. Then I designed and worked on developing computers. Some of the fastest computers in the world for special purposes. And 40 years ago, I come to this campus as an assistant professor. I was a rector 10 years, and also later I become a professor here. In the 1980s, I worked on cybernetics, signal theory, and system theory. And so after the rector period, I started to study this lunar nodal tide influence on climate and ecosystem. And from later, I started also on artificial intelligence in 2000, swarm intelligence and smart cities. And after this was the foundation of the master program in simulation and visualization. And after retirement, I started to study solar variability and climate modeling. It was a continue from my doctor thesis. I started back to my thesis to continue the work for 10 years earlier. So how it all started? Well, this is a picture from Ålesund, the good old days. The fishery was growing and everybody was happy until the fish disappeared. And then they started a discussion, who's to blame? Is it the fisherman, it is a marine scientist, or is it the nature? And some from the fishing industry, they came to me and said, Harald, we don't trust the marine scientists. Can you compute the biomass for the next 10 years? Oh, I said, in the next 10 years, this is $1 million question. But I said, okay, I will give it a try. Because I come from cybernetics in Trondheim, where Balkan, he had talked a lot of marine quota management. So to compute something deterministic, it's not easy. And I have to go back to the verse from Francis Bacon. He said, the motive of science is to predict the future, to control the future. But the key question is the future deterministic? If you don't have something deterministic, we can only explain the past. It is so simple and so easy to forget. To compute the future, we need to rely on something deterministic in the data. And I started, what can be deterministic the next 10 years? Well, the first thing I was thinking about was the tide and Earth rotation. And I found out that the Earth axis has a wobbling in a period of 18.6 years. And this wobbling of the Earth axis introduces a lunar nodal tide in the same period. It has a maximum at the pole and at the equator. So it's a stationary tide between equator and the pole. And when we had a stationary cycle of something, I knew from electronics that it would override all random fluctuations. So maybe this tide can be the source. The next step was to analyze this. And here is a simple process. I start. If they have a solar system, it has a set of periods. It's like a clock. Each period has a distant period, and the pointer is the phase information, the timing. And if this introduces the Earth, you have the climate periods. And the climate periods may be monitored in data series. So the data series is the footprints of climate variability. And the next step is to analyze the climate variability to identify the climate signature. Or the climate signature is a fingerprint of the source of the climate variation. So that is very important to understand the signature. The signature in data series is what producing the data. This is same we are studying in cybernetics. So if there is, it's like a clock in the spectral analysis, the period and the phase in information, you know the source. And if the source are deterministic, then also the climate periods are deterministic. So the whole key in climate analysis is to look for something deterministic. I knew that the Russian scientists have monitored the data in the Barents Sea for 100 years. So I contacted the Pinro Institute in Murmansk, and I had a cooperation with the Russian scientists for 2 years and analyzed their data series. They are monitored, but they had not analyzed this data set. So I helped the Russians to analyze their own data series. So this is a temperature in the Barents Sea from 1800, and you see there is a fluctuations. It looks random. There is a maximum at about 1940, and there's a cold period in 1970. It was at this period the biomass collapsed in the Barents Sea. So that it shows a direct relation with the collapse of the biomass and the temperature in the Barents Sea. Here, the next thing I did was to make a wavelength spectrum analysis. And this was 20 years ago. And for 20 years ago, I was the only one who used the waveless spectrum analysis. This was a known knowledge from oil industry. And what's key in waveless spectrum analysis is that the discovering of the phase information. When most scientists use the Fourier spectrum analysis, which found it's in Fourier analysis, you only find the frequencies spectrum is a correlation between a sinus period and the data series. But the wavelet analysis is a correlation between the data series and a moving peak period. So when this period is moving over the data series, you can find how these correlate by step. So you see on this figure that the wavelength spectrum, it identifies the peak at 1945 and the minimum period at about 1980. So this is a long period was identified and a short period. So this wavelength spectrum has ability to not only the period, but the event when the period are changing from negative to positive state. And the next step is to identify the fingerprint or the signature. So this is the autocorrelation spectrum of all the wavelengths in the wavelength spectrum. And you see here, there is a peak at 19.6 years. So there is a correlation to this period, 18.6 year. And there is a maximum correlation for 74 year, which is a fourth time the period. So if you see all the correlation, you see that there is a lunar-driven signature in the Barents Sea. It's 18.6 years one time, but also the half period at about 9 years, 2 times the period, and a 4 times the period. And they stopped at the 4th time because this is too short to identify longer data set. So this is very interesting that the climate variability in not only Barents Sea, but only in Scandinavia and in North Europe, it's controlled by a spectrum which boils down to one number, 18.6 years. So the whole spectrum boils down to this data series for then this signature and which is controlled by the lunar nodal tide. So this shows that the climate variability is controlled by the moon, because the lunar nodal tide is controlled by the moon. And next step, here is a data series of biomass cod from 1860s, 65, and you see there is large fluctuations, and that the red dot here, there is a minimum, and that is the time when the biomass collapsed. It collapsed at the time when there was a minimum temperature in the Barents Sea. It looks random, but if you analyze this, you find the fingerprints or the signature. There is a 6-year period, 18.6 period with the lunar nodal tide, and a 55-year period. So what I found out was that the North Atlantic cod signature had a lunar-driven period spectrum of 18.6 years, a third of a harmonic, and a double harmonic, also the double period, and a third of 55 years. So the biomass fluctuation in a period of more than 100 years was controlled by the lunar nodal tide. So the biomass in the Barents Sea has a deterministic variability controlled by the tide. I also analyze much more temperature on algae and capelin, herring, and all the fishing in the Barents Sea had the same signature. And here is an explanation from the fluctuation of the cod I found out that the cod biomass is period and phase locked to the 18.6-year lunar nodal period. The moon is controlling the temperature inflow to the Barents Sea in 18.6 years. And this biomass stock has solved an optimization problem by recruiting in period of about 6 years. By recruiting every 6 years, you can recruit 2 times in the warm period and 1 time in the cold period. And in the warm period, the recruitment was about 20 times higher than recruiting in the cold period. And the accumulation of the biomass then have a period of about 18.6 years. And this period, again, are multiplying in periods double and third times at about 55 years. So the biomass stock solved the optimization problem by adapting to long-term temperature fluctuations in the Barents Sea. The North Atlantic water are follow in the coastline, and you see here that it moves the Arctic ice edge position, also the ice extent. In the warm periods, it moves the ice edge position at the red line north, push the edge north. And in cold period, they are on the blue edge here, and even at the green. So in very cold period, the ice edge are moving very close to Norway. So, and the question was, what influences this edge position? This is a data series of edge position from the 15th century, 1579 to 2020. I did this analysis last year, and there are some interpolation there, but it's good enough to make a fair analysis. So what this data series shows of Arctic ice positions, it shows the signature of the lunar nodal tide. Because when the temperature of North Atlantic waters have influences by the lunar nodal tide, you see the same signature in the Arctic ice age positions. It has a fluctuation of 18.6 year and 75 year. And on this long data series, we also see there a period of about 220 years. So the ice age position in the Arctic is also controlled by one number, a spectrum related to one number, 18.6. It's amazing. And this is violet power spectrum. When you compute the violet power spectrum, you see the concentration of the large fluctuations. And you see on the right side, the power had a maximum at the warm period in 1987. And the cold period has a maximum at about 1849. And the shift at the minimum, there was a climate shift. There was a climate shift at the 1910. And we go back earlier, there was a temperature maximum again at the 1725. And there was a cold period at the 1645, also had a cold period. You see that the ice extent in Arctic is not constant. It follows long periods, and this long period fluctuation is a harmonic also to this 18.6 year time. It's a 12 harmonic of 220 years. And if we show that this is a deterministic period, we may expect that this period will continue in the future. And if it continue in the future, we will have a next cold period at about 2072 AD, and the next warm period at about 2184 AD. So the longer period you have, the longer period in the spectrum related to the lunar tide you are identifying. If you summarize this lunar spectrum, what I found out, so I identified the lunar tide. It follows one on F, the importance of one on F. You have the 18.6 years, and you have a double harmonic, 3 year, and the fourth harmonic was 74 year. 220 are found in Arctic. 440 year are found in Greenland data series, and even 220 year also in a spectrum for a lunar northern tide. So I found that the lunar northern tide signature are producing a spectrum up to 2,200 years. And climate is a sum of all these periods. And what makes it difficult is that each of these periods has different phase relations, and they have not the same phase relations every time. They have never the same phase relations, and that is why it's so difficult to identify the climate variability. It looks chaotic, but it is deterministic because they are controlled by a deterministic source. If you are interested in this research, I have a blog. My blog was removed from the webpage of NTNU, so I made my own. I call it Climate Clock. And I have explained more the Arctic and global warming. And I also have tutorials. If you go up here, you find tutorials explain what is wavelet analysis. So here I explain my methods. And on the library, I have all my publication of the subject. You can find that, and also presentation for a number presentation on international conferences. So if you are interested to know more background about this, you can read more about on this blog. When you have identified the climate signature, and if and only if the source is deterministic, then you can start working on a climate model. And here is a concept model I'm working on. You have the lunar nodal. When the lunar nodal tide is known, then I can make a lunar nodal model which produces this lunar nodal tide, and I can predict future events. And the same from the solar system. When I identified the solar spectrum, solar irradiation spectrum, I can make a solar forcing solar irradiation model. And when I have solar irradiation, I can make a model of how this solar irradiation influence on the temperature in oceans. And when I had the solar irradiation models, I can model where this signature comes from, which I have identified in the solar system. To understand the solar system, climate influence for solar system, you have to understand the periods from the planets. When I started working on this, I believe that the sun is a fixed post in the sky, and but there is a barycenter between the planets and the sun, and the sun are moving around this barycenter. So I analyzed it, not only the periods of the planets, but also how the sun are moving around this barycenter, and analyzed it also how this movement are related to solar irradiations. And what I found out, there had a coincident period of 2,285 years. And by this way, I made a solar irradiation model with periods up to 4,000 years, 4,285 years. And in the spectrum, subperiods of 300 and 500, 1,000 years, and 2,000. So there is a spectrum of periods. And the explanation is that the periods have a more the planets have more influence on the solar position around this barycenter when they are related to the perihelion. When they are closest to this barycenter, the maximum speed and maximum influences on the speed of the movement on the sun. I presented this investigation last week on EGU General Assembly. I had this presented UV planets' influence on the Earth's temperature variability. UV planets is the four large planets. IGU means last week there was 18,000 on this conference during a week. So it was a big conference. So the basic idea here is that the solar irradiation from the sun is not constant. So this data series I got from NASA. I have contacts in NASA working on satellites monitoring data series in NASA, and they gave me this data series, which shows fluctuations from 1700 up to 2014. And I analyzed this data series. I found the fingerprints from the planets. And when I had the fingerprints from the planets, I could find a spectrum. When I had a spectrum, I can make a solar irradiation model. And when I have the solar irradiation model, I can make a climate model, and also have a lunar model. I can study the interference between solar forced irradiation and lunar forced irradiations. And here you see the results. It influences the Arctic temperature. I will talk more about this. So here is the analysis which I published in 2017 in New Astronomy. As far as I know, this was the first time this was published, a direct relations between solar irradiation and the planet movements. And I was able to identify this by identify this spectrum of this signature from this data series. You see here there is a maximum here at 11 year. 11 year, this is a period of Jupiter, a maximum, and 29 year is a period of Saturn. 84 year is the period of Uranus, and the long back here is period of Neptune. So this was the identification of the signature of the planets in the solar irradiation from the sun. So what's very important from this discovery was that the solar irradiation from the sun is deterministic and can make a model of and this data series is only from 1700. When I know there's the period from the planets, I could make a model of a longer period of to more than 4,000 years. So here is the planet. Here is the solar positions oscillation around the sun. So I also made a model of solar movement around the sun. And here is so explanation is that when the solar position or rotation around this barycenter, it moves the solar dynamo. And when you are moving the solar dynamo, it's Maxwell's equations. It influences irradiation from the sun surface. And when I have the spectrum, it's here, I can make a transform. It's the same way as we do in cybernetics. So I can make a spectrum transform from the UV and planets into the spectrum of the irradiation from the sun. And from the sun, I can also make a spectrum to how it influences the the accumulation of heat in oceans. Here, I made a model from 4 planets, but here is this analysis shows only from 2 planets, Uranus and Neptune, which has the dominant influences because they have longer periods. And this is a 4,000-year simulation. And at the maximum here, 500 years before Christ, there was a maximum irradiation from the sun from this. What is interesting is that the glaciers here in Norway started to grow 500 years before Christ. And here is the minimum, envelope minimum. It has a minimum at about 1549, the coldest, and the glaciers in Norway has a maximum extent at the same period, at about 1545. So what you see minimum and maximums is a fluctuation between cold and warm period. So in this envelope period, there was a maximum here and a minimum here. What is called the Little Ice Age is between at the 1200 and 1850. And this shows there has been 5 cold periods in this time period. And here you see there is an expected next cold period. So this shows that these cold periods in the Little Ice Age is not over. There may be more cold periods in the future. The solar irradiation from the sun, minimum and maximum periods, are known from measure in data series, and they are so known they have their own names from the year 1000 AD. The first is called the Ort, the Wolf, Spører, and Maunder. Maunder is a very cold period in the coldest period, the coldest period in 4,000 years. And the modern is at about 1650. And here is the next upcoming. What is interesting is that this model, based on Saturn, Uranus, and Neptune, shows exactly the position of minimum of these cold periods. Solar irradiation from the sun and climate is not the same. And because the solar irradiation introduces accumulation of heat in oceans. It's like currents in the condensator. There is a phase delay of about 90 degrees. So this means that when you have a minimum irradiation from the sun, the accumulation of heat in the ocean is reduced on the fastest speed. This introduces a phase shift from the warm period and the cold period. So now the deep minimum in the accumulation of heat in ocean, which is computed from this model, is at about 1317 before Christ. And the warmest climate period now is at about 1030 AD. And here we have a cold period at about 1850, and a modern warm period, which we have now, is at about 2030. So this model says that the turning point of the global warming is at about 2030. It's not far away. And the next cold period is at about 2075. So what is called the global warming is this changes on this figure from this cold period here and up to this position here. So if you see in the long perspective, there has been a number cold and warm period. And this number cold and warm periods are confirmed in real data. And also what is interesting here is that this is not a random relation. This is deterministic periods controlled by the planets. So how does this fit to real data? Well, at the left side here is the global temperature from 1850 to 2000. The yellow here is the mean global land temperature. The blue here is mean global temperature, and the red one is the sea temperature. So this red dot you see on this slide shows the cold period here at the 1950, and the red warm period was up here. So here is the period change between this controlled by the solar system. So it was the solar system influences this long change of temperature here. On the right side here, we shows the global mean temperature wavelet spectrum. And when we show the wavelet spectrum, you see that there is a maximum in 1945, and cold here in 1911. So there is fluctuations. There is a climate shift in 1962 and a minimum in 1979 when the biomass of cod collapsed. If we compute the signature and the autocorrelation, we found some interesting periods. We have this 9-year, 29-year, 27, 37-year, 47, yeah. So this boils down to a lunar spectrum signature of 18.6 here, computed in 9, very accurate. The double and 65, which is interference between two periods. And here is a solar period of 29 years. So the signature of the global temperature from 1800 has the solar lunar periods. The lunar periods is the dominant periods, and the solar periods are controlling the amplitude of the lunar periods. So the total spectrum between the solar and lunar periods is interference. And because it's interference, it's so difficult to analyze these data series. But it shows that this wavelet spectrum analysis is very accurate. It's so accurate, it's from these deterministic periods in the climate models, it's less than 10 years between the deterministic computed maximum and minimum and the real monitored data. And this is a climate model which cover a total period of 4,000 years. Here is a wavelet phase spectrum. Sometime you wish to be interested to look more on the phase spectrum. This phase spectrum shows the timing of the phase shift when a parent goes from minus to plus. Here, for example, was a climate shift period at about 1865. Here is a long period climate shift and global. So here is a long period climate shift. Here is a shorter period of climate shift. This means that what is climate shifts is dependent on how long the data series. The longer data series, you find longer periods. This is a Greenland temperature data series from 2000 before Christ. It shows large fluctuations, which seems, it looks deterministic. And here we see the period of the little ice age. The temperature is reduced from at about 1200 to 1850, as I showed you earlier. So in this period was the coldest period in 4,000 years. Here is the wavelet power spectrum of the same data set of the Greenland temperature. It was a cold period here, cold period at 1700. 1750 had a maximum. It was a warm period, a cold period at about 1300, and a warm period at about 1100. And the little ice age is this period time from 1200 and out to 1850. And also here is something interesting. The minimum here at the 1600 was a phase shift from the warm period to the cold period. And at this time was the timing of the coldest, the minimum irradiation from the sun. So why was this cold period here? And why was this smaller amplitude of the violet power spectrum here? What I found out, it is interference. Interference between solar forced periods and lunar forced periods. In this time period here, from 1000 up to 1600, there is what is known as destructive interference between solar forced and lunar forced period. Destructive interference means that lunar forced periods are positive at the same time as solar forced periods are negative. They are against each other. But in this very cold period here, the coldest period in 4,000 years, at this time period, there was interference. They had the same polarity. They were negative at the same time.
So Harald, you have 2 minutes. So
Yeah.
if we have some
Yeah.
questions at the end.
So this is also the longer periods, cold periods in the Arctic. And we have temperature in wavelets from, it's like a map of long periods in the phase spectra. So, summing up, so what I say, it's this is a glacier from Ludasbreen. I think the Ludasbreen will be back. The winter is coming. Thank you.
Thank you very much, Harald. I visited that place, in fact, last year, and people are worried that it shrinks with time because of global warming. So, so thank you very much, Harald, for this nice presentation. So, do we have any questions from our audience? Any questions to Harald? Please raise your hand if you have any questions. Okay, so I have a question, Harald. So global warming, should we blame human activity, or should we blame the solar system? Because as you mentioned today it is the solar system who is responsible of the global warming.
We can't not stop the global warming. It's a part of the nature. So if to stop the global warming, we have to stop the moon and the sun and the solar system. But what we can do, we can local, we can take care of the environment. So we can take care of the environment, the ecosystem, and what is green should be more greener. But we cannot stop the climate. The climate has fluctuation of all the time, that will continue. Mm-hmm. So this is what I find from the data.
Mm-hmm. Also, I have a question. Do you have some new data after this COVID or this pandemic? For example, regarding this ice age position, do you have some new data so we can see that this reduced human activities after pandemic has some impact on this climate change or ice age position, for example? Is there any new data?
I have the ice age position data, yes.
Is it after COVID? Do you have some data after COVID?
I have up to 1920.
1920. So you don't have data after maybe 2021? No. Yeah.
No.
Yeah. Okay, so this is the last minute. So I would like to thank you very much, Harald, for this nice presentation today. And thank you very much for our audience, and have a great day. Thank you very much. So please, we will have a link. I will share the link with all people for a YouTube link for this lecture today. So if you want to share it with other people, you are free to share it. So thank you very much for attending our research seminar today. Thank you very much.